This screencast is looking at 2.2.8, the explanation of cardiovascular drift. So within the teacher's note, an increase of body temperature results in lower venous return to the heart, a small decrease in blood volume from sweating. A reduction in stroke volume causes the heart rate to increase to maintain cardiac output. Now, here it is asking to include reference to blood viscosity. The relationship here is that as we decrease blood volume from sweating, it's the plasma that we are decreasing the volume of. If we decrease the fluid content of blood, we then increase our blood thickness, hence increased viscosity, which makes it harder for the heart to push blood around the body, therefore has to beat more often to achieve the same cardiac output. So using a couple of notes from some sites and from a textbook, although heart rate increases rapidly with the onset of activity, providing exercise intensity remains constant, heart rate will level off. This is known as steady state. So when we can meet the oxygen demands of our working muscles. However, an exception to this is during prolonged steady state exercise, so the important word here being prolonged, particularly in a hot climate, steady state heart rate will gradually increase. This is known as cardiac drift, thought to occur due to increase in body temperature, and the increase in body temperature will then result in what we've talked about up there. So it's a brief intro. Cardiovascular drift, the changes in observed cardiovascular variables that occur during prolonged, heavy, submaximal exercise without a change in workload. So what we're looking at here is a change, and primarily looking at an increase in heart rate when the actual workload does not change. And of course, prolonged submaximal exercise. So we'll look through this. Left ventricular end diastolic volume increases because of the return of blood to the heart by the active muscle pump, increased venoconstriction, which decreases venous pooling, thereby increasing venous return and increased cardiac output. This is what happens as we exercise. So as we exercise, we increase with an increased venous return. Left ventricular and end systolic volume decreases owing to augmented contractility of the heart, which effectively ejects more blood from the ventricle, leaving a smaller residual volume. So as we exercise, we pump out more blood, so our stroke volume increases so that we can increase cardiac output and meet oxygen demand. However, if exercise continues beyond approximately 30 minutes, stroke volume gradually drifts downwards, although it remains elevated above resting levels. The downward shift in stroke volume after approximately 30 minutes is most likely due to thermoregulatory stress, meaning increase in temperature, body temperature, plasma loss as a result of sweating, and also a redirection of blood. Now, the redistribution of blood means that we're distributing it away from the working muscles where we actually need it for oxygen, but towards the skin so that we can try and dissipate the heat or the extra heat that is being produced. So this effectively reduces venous return and hence causes a reduction in stroke volume. As stroke volume drifts downwards, what we find is that we have the opposite with the heart rate. Heart rate displays a pattern of initial increase, plateaus at steady state, and then shows a positive drift. Remembering that we're trying to maintain cardiac output, which equals stroke volume times heart rate. So if we have a decrease in stroke volume, so a negative drift, then we have to have a resultant increase in heart rate, so a positive drift. I'm just going to let you pause this and continue to read because we've gone over the majority of what we need to, or we have gone over what we need to. Move it down further so you can read the remainder of it. Okay, we're going to look at this aspect here, where what can be seen to be the best way to combat cardiac drift is by maintaining fluid. So this was a study that looked at cardiovascular response to long-term moderate to heavy exercise, so looking at 70 to 76% VO2 max and without fluid replacement. So the red line being fluid replacement, we can see here that our cardiac output when we had or replacing fluid increased, whereas without fluid replacement our cardiac output dropped. Our stroke volume showed quite dramatic negative drift, a decrease, with a resultant quite dramatic increase in heart rate to compensate. So as can be seen here, fluid replacement, cardiac output grew a little, stroke volume, it increased initially, then just the slightest decrease, but heart rate did increase, but nowhere to near the same degree as what without fluid was. So, moral of the story, if you're doing continuous activity over an extended period of time, make sure that you replace your fluid so that you maintain blood volume